Hello, my name is Brian Ogle, and this is my webinar project for Forestry, Wildlife, and Fisheries 590, Dr. Zobel's class at the University of Tennessee, Knoxville. I'm going to start off with a little background about myself. I am the assistant groundskeeper for football operations here at the University of Tennessee. I work for the athletic department. My job duties consist of taking care of Neyland Stadium and Haslam practice fields. I am responsible for mowing, fertilizing, and the overall care of the fields. But I feel like the most important thing that I do is I'm in charge of painting the fields for game days and all other events that we have on the fields. I'm the person that paints the checkerboard end zones, and I paint the Power T and the SEC logos. I also help out with painting the lines and the numbers, hash marks, and the border. I'm also a graduate student for plant sciences under Dr. John Shirakin. I've worked for the grounds crew for 13 years now, and while I've been painting, I've seen how the amount of paint that I use on the end zones and the field, how it affects the grass in the spring, and also the paint moving down into the soil profile. Normally what I used to do before I started this project was I would normally use 30 gallons of paint per color per end zone. So I would use 30 gallons of white and 30 gallons of orange for one end zone. If we do a little bit of math here, that's 60 gallons of paint per checkerboard, 2 end zones. That jumps up to 120 gallons of paint for the 2 end zones itself. That's not counting the numbers or the lines or the T or the SEC or the border. That is just 120 gallons of paint just for the end zones alone. I learned to spray them at 1200 to 1500 psi, and I would use different sizes nozzles depending on which one I felt put out the best product. Like I said, my master's project was to figure out how this athletic turf paint that I've been spraying on the grass affects the soil profile and the roots of the turf grass plant. This picture here is one of the first times we resodded the field, and as you can see right through here, you can pretty much see the exact outline of the checkerboards. And this depth was cut about 2 to 3 inches down. We have dug down to almost a little over a foot, and we still found that these squares went straight down. You could still find orange on one side and white on the other. Not only am I painting the end zones for the football games, I'm also painting them for recruits and camps and special events throughout the year. I end up painting the checkerboards anywhere from 10 to 15 times in a calendar year. If we do some math, 120 gallons of paint used times 15 times, that's 1,800 gallons of paint that I'm spraying on the end zones alone. And this paint has to go somewhere, and it's leaching through the soil profile. And what I'm trying to find is how we can minimize this leaching of the paint through the soil. What I did to start my master's project is I did a nationwide survey from other head groundskeepers around the country, professional and college groundskeepers, just to find out what everyone else is painting their fields with, what type of paint, what pressure settings, what nozzle settings, what type of machines, what days are they using it, how many times are they spraying their fields. And what I found out was it's mostly personal preference on settings. There were guys that were shooting really high pressures like I was, and there were some guys that were shooting really low pressures. There's no concrete set in stone settings that people go by. So working with Dr. Shirakin and the other plant professors, what we want to do with this study is figure out if we can lower the amount of gallons of paint sprayed. That's going to be less detrimental to the turf grass, but it's still going to be aesthetically pleasing for national TV. The information that I find from my study is going to be not only published in an article, but it's also going to be made into a guidebook to give to these groundkeepers around the country. And not only just these high-profile college and NFL, but we want to help the high school football coaches that have to spray their own football fields, people that take care of rec sports, even church leagues. We want this information to be sort of a guideline of how to set up a sprayer and how to set up a paint machine and not be detrimental to the turf grass itself. This is a quick shot of my study plot. I did 6 different treatments with 3 replications, and I did this to mimic the end zone squares. Every time that I would paint the end zones, I would come out to the UT farm at the Center for Athletic Field Safety and spray these squares just as I would the checkerboard end zones, using different nozzles and different pressures. For my control, I took soil samples before I applied any paint at all to the grass. These samples were subject to find bulk density, micro pore space, micro pore space. We did some infiltration readings and found out the organic matter content in these soil samples. This is a soil sample taken from after the study was concluded, and as you can see right through here, this is the white paint that I sprayed, and this is after a 13-week period. This paint right through here had already moved down into the soil profile about an inch or so. If you think about this over, say, 10 years, just think about how much this paint is going to move down the soil profile. Dr. John Zobel helped me with my statistical analysis, and I used a randomized complete block design, and we're comparing the bulk density of the soil samples before and after the paint applications. We used nozzle size and 3 different pressures as the factors, and we just did a simple analysis of variance. ANOVA was used to determine if the nozzle size, the pressure setting, or the nozzle times the pressure setting were significant in affecting the bulk density of these soil samples. And I will show you what I did in R right now. Okay, again, Dr. John Zobel helped me set this up using R. We took my data here from nozzle. Here's all my data set that I had of bulk density, organic matter, macro, but I was really just worried about the bulk densities because this is what affects the root growth of the plant. We put it in a linear model. We did bulk density from nozzle plus pressure. We squared it plus a rep, and we put this into the ANOVA AOV, and then we did a summary. We'll do a summary right now, and this gives a summary of the ANOVA table. As you can see here, my p-values for nozzle is a 0.0742. For pressure, it's a 0.68. For rep, it was 0.26, and nozzle times pressure was 0.58. Well, this is showing that in the first year of my study that pressure, rep, and nozzle were not significant. However, nozzle was. So this is saying that going from a small 319 nozzle size to the 421 in the first year was significant, which would make sense because the larger the nozzle size, the more paint you are putting on the turf grass itself. We also, this is a summary table of the bulk density of my treatments. This is the this is the mean control of bulk density of my 2 nozzle sizes, my 3 pressures I use, and these are my 6 treatments that I used. And as you can see here on this next slide, this is a box plot showing the bulk densities of all these treatments. 0 right here is my control. 1, 2, and 3 are small nozzle sizes, and 4, 5, and 6 are my larger nozzle sizes. And as you can see right here, the 4 and 5 treatments all had a little bit higher bulk density, average bulk density, than the rest of all the treatments. So I thought that was interesting. As an alternative analysis, I used MRPP from the vegan package. MRPP stands for multiple response permutation procedure, and it's using a test to whether there's a significant difference between 2 or more groups of sampling units. It calculates algorithm for all pairwise distances in the entire data set and calculates a thing called delta. Basically what I got was that MRPP procedure calculates the difference between all the observations within the groups or factors, and it generates a average distance for each group. This sort of represents a signal, so the smaller the average distance, the stronger the signal. Then MRPP generates noise by randomly shuffling the class variables within the data set. So now the weighted average of the distances within the random groups are recalculated, which is what the noise is, and this reshuffling, or what they call permutation, is repeated, a 1,000 times until you get a distribution of the average distances. Then it calculates the probability of randomly getting a smaller distance than the average distance for the true groups. And this is what gives you a p-value, just like it in ANOVA, which would test significance or not. And I will show you that in R now. The only downfall I found about MRPP is that you can only run one factor at a time. So what I did here, this is MRPP. I'll show you the help for it. First, and it requires a data matrix from data, a grouping, which is your factor or factors, your distance. The distance you can change. I found I use Euclidean, but there's Bray, binomial. There's all different distance measures. Like I said, I use Euclidean, and there's all different parameters here that you can change, but I just kind of left it alone except for Euclidean. And what I did here was I used nozzle, my data set, the grouping I used nozzle, and the distance I used Euclidean. So I will run it here, and this is what MRPP gives. Let's show this where you can see. Disassembly index is Euclidean. That's what I told it to do. Here are my two nozzle sizes, 319 and 421. It gives the delta 516.3 and a 515.4. Chance corrected within the group agreement of alpha is negative 0.005, and right here is the observed delta from the expected, and as you see here it says the observed delta is 515.8 with the expected delta of 513. So this kind of, my data is kind of a little bit over what the expected premonitions told it would be, and the significance of delta here is 0.45. And right here's number of permutations was 909. It ran this 999 times to get these observed and expected, or the expected deltas. And then for my that was for nozzle. For pressure, we'll run same thing, MRPP grouping for pressure factor, and then I use Euclidean again, and we'll show what this says. There's my three pressure settings. Chance corrected within the group agreement is 0.72, a lot higher than what the nozzle was. But right here, the observed delta was 141 with the expected of 513. And the significance of delta is 001. So I'm taking that as this is not significant enough, and it's not even close to the expected delta. So I'm presuming that delta, or that the pressure setting is non-significant. And then for lastly, I did MRPP right here, nozzle treatments, and I did Euclidean again, and we'll run this. As you can see here are my treatments. The chance corrected within a group agreement is 0.3522, which is a little bit lower than the pressure settings. But the observed delta is 332, and the expected is still 513.2. But right here again, the significance of delta is 0.001. So I'm going to call that as not significance either. So in closing, it's showing my NOVA and my MRPP procedures showed that nozzle was significant and my pressure setting and my treatments were not. This would hold true. This is on my first trial run of this project. I hope to repeat it at least 2 more times to try to get 3 years of data to figure out and see if the pressure setting with the nozzle type, or nozzle size, I'm sorry, turns out to be significant in the latter years of this study. The ideal of this study is that high pressure large nozzle is going to put out a lot more paint than a low pressure smaller nozzle. And we're going to do some different digital imagings and other tests on these upcoming trials to just see if we can tell a visual difference between the high and low pressure or the smaller nozzle versus the larger nozzle. Again, my name is Brian Ogle. I would like to thank Dr. Zobel for his help this semester with all this stats and the help with R. And in closing, I'll say go Vols. Thank you very much.